Welcome to Applied Physics series, where we will focus on waves and oscillations. Here's an outline of our video today. This structured approach will guide us through foundational concepts and applications. Wave motion describes the transfer of energy through a medium without a permanent transfer of matter. As energy moves, particles in the medium oscillate around their equilibrium positions, forming patterns that propagate outward. A common example is ripples created by dropping a stone in water, where energy radiates outward without moving the water itself to a new location. Waves are classified based on how they propagate. Mechanical waves require a medium, like air or water, to travel. They come in two forms. Transverse waves. Particles oscillate perpendicular to the wave's direction, like waves on a string. Longitudinal waves. Particles oscillate parallel to the wave direction, as seen in sound waves. Electromagnetic waves don't require a medium, allowing them to travel through a vacuum. These waves involve oscillating electric and magnetic fields perpendicular to each other and the direction of propagation. As you can see in this diagram how in transverse waves, particle motion is perpendicular to the direction the wave travels, creating crests and troughs. In contrast, longitudinal waves involve particles moving parallel to the wave direction, producing compressions and rarefactions. This distinction is crucial in understanding wave behaviors in different contexts. Waves have several defining characteristics. Wavelength, lambda, the distance between two consecutive points in phase, like crest to crest. Frequency, f, the number of oscillations per unit time, measured in hertz. Amplitude, a, the maximum displacement from the mean position, indicating wave energy. Wave speed, v, the speed at which a wave travels, calculated as v equals f times lambda. For example, a sound wave with a frequency of 440 Hz and a wavelength of 0.78 meter in air travels at 343.2 meters per second. In this diagram, you can have a better understanding of the different characteristics of the waves. Simple harmonic motion, SHM, is a type of oscillatory motion where the restoring force is proportional to displacement and acts in the opposite direction. Represented mathematically as F equals minus kx, where F is the restoring force, k is the spring constant, x is the displacement from equilibrium. The oscillatory motion is sinusoidal in nature and has the following properties. Period, t, the time for one complete cycle. Frequency, f, the inverse of the period, or f equals 1 by t. Phase, phi, indicates the position within a cycle. SHM is sinusoidal, reflecting its periodic, smooth oscillatory nature. In this diagram, you can understand graphs showing the sinusoidal pattern of SHM displacement over time. A mass spring system is a classic example of SHM. When stretched or compressed, the spring exerts a restoring force on the mass, moving it back towards equilibrium. The mass oscillates as energy continuously transfers between kinetic and potential forms. This motion depends on the mass and the spring constant, defining the system's frequency and period. The motion equation for a mass m on spring with spring constant k is given by xt equals a cos omega t plus phi, where a is the amplitude and omega equals under root k by m. This diagram represents mass spring system with forces showing equilibrium and displacement positions. A simple pendulum also exemplifies SHM under small displacements. Gravity provides the restoring force, pulling the pendulum back toward its equilibrium. Like the mass spring system, the pendulum oscillates with a period depending on its length and gravitational acceleration, highlighting SHM's consistent principles across different systems. The period of a simple pendulum is given by equals 2 pi under root L by G, where L is the length of the pendulum, G is the acceleration due to gravity. A simple pendulum motion is explained by this diagram. The wave equation mathematically describes wave motion, representing the relationship between wave speed, wavelength, and frequency. For mechanical waves, this equation integrates medium properties, while for electromagnetic waves, it incorporates electric and magnetic field oscillations. Understanding the wave equation is essential for analyzing wave propagation in various media. A sinusoidal wave's displacement yxt can be represented as yxt equals a sine kx minus omega d plus phi, where a is the amplitude, k is the wave number related to wavelength, lambda, by k equals 2 pi by lambda. Omega is the angular frequency, given by omega equals 2 pi f. Phi is the phase constant. This function describes how the wave varies with position and time, illustrating wave progression. The superposition principle states that when two or more waves meet in a medium, the resultant displacement is the sum of their individual displacements. This principle is foundational in wave interactions, allowing constructive and destructive interference that creates patterns in sound, light, and water waves. Mathematically, if two waves are represented as y1, xt, and y2, xt, their combined effect y total at any point is y total equals y1, xt, plus y2, xt. In real-life scenarios, wave interference is common in sound, light, and water waves. Interference effects are used in various technologies, including noise-canceling headphones, radio signal tuning, and laser applications. Constructive interference occurs when delta phi equals 2n pi, where n is an integer, resulting in amplified sound or light. Destructive interference occurs when delta phi equals 2n plus 1 pi, causing partial or complete cancellation of sound or light. For two waves with the same frequency and amplitude, the interference pattern is determined by their phase difference. Delta phi equals 2 pi delta x by lambda, where delta x is the path difference between the waves and lambda is the wavelength. That's it for today's video. Thank you for exploring waves and oscillation with us. We will look at electromagnetic waves in the next video. Do subscribe to the channel and like the video.